All right. here's the deal. All right. As we saw in the circuit, oh gosh, dang it. Let's check out my email again. Quit that. Go away. All right. Now, hopefully I don't get any texts. Those are always embarrassing. Anyway, the junction rule states that the total current directed into a junction must equal the total current directed out of the junction. This is kind of like your calorimetry problems. The amount of energy going in is going to equal the amount of energy coming out of a system. Okay. As a matter of fact, this is not a conservation of energy thing, though. Remember this: Kirchhoff's rules, conservation of charge. I bet $1 to a donut. I'll bet $10 to one donut that, that you're going to see something like that on the conceptual part of the exam. It's conservation of charge. The amount of charge coming in is equal to the amount of charge coming out. Okay? All right. So, the loop rule, and the loop rule is this: when we go around the loop of a circuit. Okay? So this is 12 volts. Boom. Kicks out 2 amps. Now notice, this is a simple circuit. This is a pretty simple circuit. So we've got a voltage drop here of 2 times 5, which equals 10 volt drop. So there's a drop. Then it comes along here, and we've got a voltage drop of 2 amps, IR. 2 times 1 is 2 volts. So now it has no energy. It comes here. Boom. Kicks out again and comes around. Loop rule, conservation of energy. Loop rule, conservation of energy. Junction with the sum of the magnitudes of the currents directed into junction with the sum of the magnitude. Okay, so there's the two rules right here. Conservation of charge, conservation of energy. All right? Determine the current in this circuit. Okay, so we'll look at the loop. Well, first of all, the junction rule tells me there's no junctions. So I've got to look at the total. So I got 24. Now look. So I've got, boom. I've got an increase of 24. I've got a drop of 12I. 12 times I. Okay. So it starts here. I'm going to start on a negative node. Boom. Gain 24. Dropped 12 times I volts. Dropped 6 volts because I'm going against it. This is facing the wrong way. So basically I got 18 volts. Dropped 8I. So to determine the circuit, I've got 12I plus 8I. Those two voltages are dropped. That's a total of 20. Then I've got 20. Then I've got another drop. So the gain was 24 is equal to 12I plus 6 plus 8I. So that's 20I plus 6. And so I subtract, get 18. And for both sides, I solve. I get 18. It's 0.9. Because here's what I was talking about. So you go to 24. You solve for I here. Piece of cake. This one's much trickier, and we'll do that one. But we do the same thing. We pick a loop. We're going to solve 3 equations, 3 unknowns for this to figure out, because I've got 3 currents that I need to know. Okay. And I'll show you how to do that. It's going to be a video all itself. All right. Draw the current. We'll do all this. Okay. Here's the other thing. Measuring voltage and stuff. It's magic on how we measure things, so don't worry about it. Okay. Amp meters, voltmeters. Okay. I don't worry about that. Now, let's talk about capacitors in series and parallel. Okay. Here's the big idea. So we're not doing any of that how to measure things. Okay. Capacitors in series and parallel. All right. So here we go. I've got capacitor here and a capacitor. Notice they're in parallel. Also notice what happens is the Q is not the total charge in this circuit is Q1 plus Q2, because remember there's built up charge here of Q1 and a built up charge here of Q2. But they may or may not be the same. If these two capacitors are the same, they would be, but they're not. Okay, so, but we know that Q is equal to the capacitor times the voltage. Capacitance times the, but wait, the voltage here is the same as the voltage here. Ha ha. So if I divide out the voltage, I get C1 plus C, so the total capacitance, when they're in parallel, just the opposite of resistors. You just add them. But the charge is different, but the voltage drop is the same. So what happens when they're in series? Notice the voltage drop is different. The voltage is different. And voltage, V1 plus V2, is equal to Q over C1 plus Q over C2. So therefore, pull out the Q, it's 1 over C1. So when capacitors are in series, they behave like resistors in parallel. Okay? All right. And we do all of these things are so that we can control the current inside a circuit. Okay? And last but not, I'm going to go ahead and do this one. Last but not least, RC circuits. Classic RC circuits that every health science person should know about. Every person should know. And I have to be honest, I've never been trained on one. Is a defibrillator. It charges up. And it discharges. Okay. Sound effects notwithstanding. All right. So here is a resistor. It's got to have a resistor, usually a huge resistor. And we charge up our capacitor. A classic one of these was back in the day. Sometimes this causes my thing to quit. But back in the day when we had, remember the old-timey cameras that we used? The old-timey, where you cranked them, you cranked the cameras. Disposable cameras. That's what I was trying to do. They've only been gone for about 6 or 7 years, and I've already forgotten what they. But anyway, they used this kind of thing. You'd crank it up, and that'd scrape. That cranking, what that did was that scraped a bunch of electrons off it. It basically worked like a Van de Graaff machine. They had a little Van de Graaff machine basically in the middle of that, scraping the electrons off that belt, and then creating a huge amount of charge in the capacitor. Okay, and a ton of resistance, and then boom, you'd hit the switch, which was when you took the picture, and whoosh, the current would fly through there and take that picture for you. Okay, so that's what's going on there. So it's a time dependent thing. Now look at this. What is anything to the zero power? So if t is equal to 0, what is anything to the 0 power? It's 1, right? I mean, anything to the 0 power, this whole term goes to 1. So I've got 1 minus 1. So the charge in there is equal to, for when it's charging, is equal to the initial charge. Okay? No, it's equal to 0 because I've got 1 minus 1. I've got 1 minus 1 is 0, so there's no charge. But as t goes to infinity, what happens? This term goes to 0, and so as I charge for a long time, Q then becomes Q naught. And I'll show you how to work the problems here in a little while. Discharging. Aha! Now in biology, you use population. When you're using population, in finance, they do these all the time. And the time constant that we talk about is the resistor times the capacitor. But that's what this is what this does, is we charge up something and then we use it. Boom. And it discharges really fast. Because notice this, if this is equal to 0, then this term is equal to 1. So when it's discharging, Q is equal to Q naught. Then when this goes to infinity, when t goes to infinity, this term goes to 0, and so the charge goes to 0. That's inside the capacitor. There's a pacemaker. We're actually going to do a pacemaker problem. All right, that's it. Now let's do some problems.